Hi everyone, and welcome to today's webinar. As data centers grow in size and power density, effective cooling has become a critical engineering challenge. Engineers know that if cooling systems fail or underperform, the consequences can be severe. That's why accurate, transient thermal analysis is essential for designing efficient and reliable data center cooling systems. Today, we'll explore how Flownex helps you achieve this. Performing transient thermal analyses helps engineers solve several common design challenges. These include managing hybrid systems under changing load conditions, predicting system response to rapid load ramps, ensuring compliance with strict SLAs, and delivering results within short turnaround times. Flownex makes this possible by realistically modeling both the thermal and hydraulic behavior of all mechanical and control components in a modern data center cooling system. This creates an engineering simulator that can be used to assess the performance of the system in a virtual environment. In today's session, we'll show you how these Flownex simulations are built and used. We'll look at evaluating the hydraulic performance of a chilled water system and understanding the system performance during thermal ride-through and load ramp events. Towards the end, we'll talk about some of the key features in Flownex that make it an ideal tool for simulating these scenarios. Before we get started, a quick note on the webinar interface. You'll see a questions tab on your right-hand side. Please feel free to type in questions at any time, and we'll address them during the Q&A at the end. Chilled water piping is at the heart of most modern data center thermal management systems. Performing a hydraulic analysis is a good way to understand the performance of these piping systems and is a good starting point for verifying the design of a good thermal management system. Such an analysis will help you find the required operating points for a pump selection or to verify that a selected pump would be sufficient. A sophisticated tool like Flownex is often needed for this type of analysis because cooling system piping is not a single flow path with one pump and one heat exchanger. There are hundreds of different diverging and converging flow paths, making it difficult to accurately capture all the pressure drops and flow distributions in the piping system. This also makes it difficult to foresee issues in flow distribution ahead of time. Using a detailed flow simulation tool can reveal these issues early in the design process, where changes are easy to make and won't delay the project timeline. Before we get into the detailed workflow, I just want to explain the system we are looking at. This is a hypothetical setup that has all the typical features and components of a modern data center thermal management system. There are 2 data halls with 16 CRAHs each, 3 water-cooled chillers with buffer tanks and evaporator pumps, and 3 sets of distribution pumps to supply water to the data halls. To reject heat to the environment, there are 5 dry air coolers on the roof with condenser pumps to move water from the chillers to the decks. When performing a hydraulic analysis in Flownex, the first step is always importing the cooling system piping network from the architectural model in Autodesk Revit. Flownex provides a Revit add-in that exports geometry and component properties directly into Flownex. I've already completed the setup for this demo, so you can see the exporter window is populated. The setup allows you to filter the families and types you want to be included and then proceed to map all of the components in these families to the correct Flownex components. You can use preset or custom mapping actions. Properties and naming templates can be added so that the correct component data is transferred to Flownex during the export. The exporter can automatically fix broken joints or overlaps, validate the changes so you don't get unexpected errors. When you press Build Network, the exporter pushes the geometry into Flownex. Back in Flownex, you'll see a piping system here in the 3D view with connection points for all the mechanical equipment. View nodes of the connection points have been created on different Flownex drawing pages so that each different type of equipment has its own page. There is one drawing page each for the chillers, dry air coolers, buffer tanks, pumps, fan walls, CDUs, and liquid-cooled IT racks. The liquid cooling rings with CDUs and liquid-cooled IT racks have been added into the Flownex model after the import, with 5 CDUs per data hall. For the hydraulic study, we usually use simplified mechanical cooling equipment that is only representative of the pressure loss or pressure rise of the component. When we move to the thermal ride-through studies, these components will be replaced by more detailed characterized models that accurately simulate the thermal and hydraulic transient behavior of the mechanical equipment. Starting with the imported piping model, losses are added for the various piping elements, such as tees, strainers, valves, etc. The pressure drops across the mechanical cooling equipment can be modeled in a variety of ways, including quadratic scaling losses, fixed flow rate losses, and custom chart losses. Once all the equipment is defined, we set the required flow through the pumps by using the fixed mass flow feature, as you can see here. We also set the chilled water system pressure differential in this steady state controller. Now, with the flow rate and system pressure differential fixed, the only unfixed hydraulic parameter is the pump head. When we solve the model, Flownex calculates the pump head along with the other flow characteristics. An Excel report records the flow rate and pressure drop of all the mechanical cooling components and the pumps, and this data can then be used to obtain a pump operating point. We can now also check the flow velocities and any other flow results throughout the piping system by activating various result layers. Looking here at the velocity result layer, we can see that the velocities are reasonable, not exceeding about 2 to 3 meters per second anywhere in the system. Once the pumps are correctly sized, attention shifts to more dynamic challenges, such as maintaining safe conditions during power interruptions and rapid recovery events. These events, commonly referred to as thermal ride-through events, occurs when main power is lost, followed by generator startup and a fast chiller restart. During this time, fans close down, buffer tanks switch modes, and control systems redirect flows, all of which must be captured accurately in the simulation model to predict the cooling system performance. The main purpose of simulating such scenarios is to ensure that certain temperatures, typically the TCS water supply temperatures and the cold air temperatures, do not exceed their maximum design values. If the results are unacceptable, design changes can be made in the simulation to find ways to eliminate system responses that could cause temperatures to breach design thresholds. Such changes could include resizing the buffer tanks, using mechanical equipment with better performance, or modifying the logic in the sequence of operations of the system. Since all of the mechanical cooling equipment is operating well away from nominal design conditions during a thermal ride-through, it is very important that the simulation tool which is used models hydraulic and thermal behavior correctly at a fundamental level, which is exactly what Flownex does. To demonstrate this, we modeled 2 thermal ride-through scenarios at maximum IT load under worst-case ambient conditions, with all the chillers running and no free cooling. In scenario 1, 80% of the load is cooled by fan walls and 20% by liquid cooling. In scenario 2, the split is 95% liquid and 5% air. In both cases, the chillers, dry air coolers, and fan wall fans trip during the power outage, while pumps, CDUs, and controls remain on UPS. Before we look at what happened in the first simulation, let us quickly look at the model. As mentioned previously, more detailed characterized mechanical cooling components are used for transient simulations. This has already been set up in this model, as we can see here from the components connected up on their drawing pages. Each component type is built up from its fundamental subcomponents and integrated into a compound component in Flownex. For example, the fan wall compound component that you see here consists of a characterized fin tube heat exchanger, fan, control valve, and the associated control elements that regulate the fan speed and valve opening to maintain the desired air supply and return temperatures. Let's look at what happens in the first simulation. When the power outage occurs and the chillers trip, the chiller cooling capacity decays gradually due to thermal inertia, as can be seen here on the chiller net cooling graph. The reduction in cooling, together with a sustained chilled water flow, causes chiller outlet temperatures to rise, as we can see on this graph. The chilled water supply temperature to the fan walls and CDUs, however, remains constant due to the buffer tanks, as we can see here on the buffer tank outlet temperature graph. This continues as long as the buffer tanks are discharging and providing chilled water at set point temperatures. The buffer tanks are depleted at about 3.5 minutes into the simulation, which can be seen here by the buffer outlet temperature beginning to increase. However, when we look at the chiller supply temperatures at the same point in the simulation, we can see that they have not fully recovered yet. This means that some warmer chilled water will be pushed through to the fan walls and CDUs, which we can see when we look at the fan wall chilled water inlet temperature graph here. This results in an increase in the CDU TCS supply temperature and the cold air temperature. The cold air temperature has two peaks. The first peak is during the power outage and is due to the fan wall fans coasting down, resulting in lower airflow and leakage of air from the hot aisle containment to the cold aisles. The second peak is due to the increase in chilled water supply temperature. In the first scenario, the temperature peaks of the cold aisle air temperatures are significant due to the high air heat load. The CDU TCS supply temperature peaks are less significant due to the low liquid cooling load. In the second scenario, this is reversed. Accurately modeling transient thermal behavior lets us quantify the expected rise in cooling air and water supply temperatures. These results show that the design would meet the requirements of a typical SLA and verifies that the buffer tank size is sufficient, the equipment startup times are fast enough, and the sequence of operations provides sufficiently fast control. Next, we'll look at how the Flownex model can simulate transient heat load fluctuations in a data center cooling system. Modern data centers experience load spikes when many intensive workloads start simultaneously. This could be due to AI training workloads, spikes in user demand, etc. These rapid spikes result in rapid increases in cooling demand and often result in increased temperatures if the controls cannot respond quickly enough, which may cause thermal throttling in the IT equipment. Simulating these scenarios ensures that you are confident that the system will provide TCS supply temperatures below the design threshold. It also helps identify any flow distribution issues and allows you to verify that any changes to the control logic provide improved performance. Unlike the previous thermal ride-through scenarios, this study focuses on the system's response to rapid changes in IT load, showing how chillers, pumps, and buffer tanks interact to try and maintain stable supply temperatures and prevent temperature excursions. With some minor control updates, the same Flownex network that was used for the thermal ride-through studies can also be used to simulate transient heat load fluctuations in the system. For the example scenarios that we will be looking at, the servers are predominantly liquid-cooled, with a 95% water, 5% air split. The simulation begins at 30% IT load on the liquid side with 2 of the 3 chillers staged down. At 1 minute into the simulation, the IT load is increased to 100% in 60 seconds. The remaining 2 chillers are sequentially restarted to accommodate the increased heat load. For the first scenario, a more traditional chiller stage-up criteria is used, where the chilled water supply ring average temperature is monitored. A sustained increase in temperature indicates that the online chillers are not providing sufficient cooling to maintain the chilled water supply set point, and a chiller restart is initiated to provide additional cooling. Running the first scenario, we observe unintended flow through the offline chillers shortly after the load ramp begins, as we can see from the graph here. This is undesirable because it depletes the associated buffer tanks before the chillers are online. This should be rectified before investigating the load ramp further. The reason why this happens is because, when operating in normal mode, the buffer tank isolation valves are open, creating a potential flow path through the chiller. When the load ramp occurs, the CDU PIC valves open in an attempt to limit the increase in CDU TCS supply temperature. When the valves are open, the chilled water flow increases, and the chilled water distribution pumps ramp up to supply the increased demand. If the speed increases sufficiently, the hydraulic resistance in the offline chillers is overcome, and the chilled water begins to flow through them. The solution to prevent this is fairly simple. Modify the sequence of operations control so that the buffer isolation valves and bypass valves are closed for all offline chillers. This will prevent any unintentional flow through them and force all the chilled water flow to pass through only the active chillers and pumps. Having solved the flow problem and rerun the load ramp simulation, we can now look at the results. When the load ramp begins, the TCS fluid temperatures begin increasing. This hotter fluid arrives at the CDU within a few seconds. Looking at the CDU TCS return temperature here, we can see that it begins increasing soon after the load ramp begins. This hotter fluid flows through the CDUs, causing the CDU TCS supply temperature to increase, as can be seen on this graph. The PIC valves open in response, as can be seen here on this graph, to allow more chilled water flow through the CDUs in order to increase the heat transfer and attempt to reduce the CDU TCS supply temperature back to its set point. As we can see here on the graph showing the chilled water flow rate through the chillers, the chilled water flow rate increases due to the CDU PIC valves opening. This causes the chilled water pumps to ramp up to meet the demand. As we can see here on the chiller net cooling graph, the increased flow through the chillers causes an increase in load until its maximum cooling capacity is reached. We can see on the chilled water supply temperature graph here that the chilled water temperature starts increasing above its normal set point after the chiller maximum cooling capacity is reached. From the buffer tank outlet temperature graph here, we can see that the buffer tank continues to supply chilled water at the set point temperature to the system for some time after the chiller supply temperature has begun increasing as the buffer tanks are depleted. When the buffer tank is depleted, the hotter chilled water enters the chilled water supply ring, triggering chiller stage up. However, when we look at the chiller net cooling here, we can see that it does take some time for the chiller compressors to start up and ramp up to full load, during which time hotter chilled water continues to enter the system and propagate through to the CDUs. We can see the bubble of hotter chilled water passing through the CDUs when we look at the CDU chilled water inlet temperatures on this graph. This reduces the CDU heat transfer. As we can see here on the CDU TCS supply temperature graph, this hotter chilled water inlet temperature and resultant reduced heat transfer causes the CDU TCS supply temperatures to remain above set point until the chillers provide sufficient cooling to reduce the chilled water supply temperature. Looking at the results, the inherent problem with this staging philosophy becomes apparent. The chillers only stage up when the buffer tanks are depleted, virtually eliminating the main benefit of buffer tanks. This results in some hotter chilled water being pushed through to the CDUs. Additionally, because the chilled water pumps stage up with the corresponding chillers, the CDUs are also starved of chilled water as the online pumps are unable to provide sufficient flow. These factors cause the CDU TCS supply temperature to increase to a point where it could easily exceed typical SLAs. To eliminate this problem, the chillers must be staged up before the active buffer tanks are depleted. One way to ensure that this happens is to monitor the IT load directly and base the chiller stage up control logic on this. The second scenario is set up to do this. The benefits of beginning chiller stage up before the buffer tanks are depleted becomes apparent when we look at the results. With the new staging criteria, the chilled water supply temperature increase is limited to only about 1 degree, compared to 4 degrees in the first scenario, and there is sufficient chilled water flow to the CDUs, resulting in a far lower peak CDU TCS supply temperature. These simulations helped us identify some flaws in the system design when the system responds to rapid IT load ramps. We were able to make changes to the control logic to correct this and verify that these changes produced a better system response. To wrap up, let's step back and look at what makes Flownex so effective for modeling data center cooling systems. The real strength lies in its combination of fundamental physics, advanced control capabilities, and seamless integration with other tools, all of which ensure realistic, reliable, and practical simulations. Flownex delivers realistic behavior under both nominal and off-design conditions because its models are grounded in first principles physics. Mechanical cooling equipment is built up from its most basic components, so real-world factors like pump and fan efficiencies, heat exchanger thermal inertia, temperature front tracking, and heat transfer coefficients are all captured in the model. On top of this physics foundation, Flownex includes a powerful transient solver with flexible control options. In these studies, we used PID controllers, rate limiters, trip switches, and custom control scripts to realistically represent how systems respond dynamically. This means you can test not only the equipment but also the control strategies that govern their operation. Flownex also connects seamlessly with other software. We've shown how the Revit importer speeds up hydraulic model setup, but Flownex can also couple with Cadence Reality DC. This enables detailed 3D CFD analysis when results are required at precise locations in the white space. Overall, Flownex enables faster, more efficient, and more accurate thermal system design. It enables you to verify thermal management system designs under hydraulic loads by quantifying the limits of the system during transient scenarios and helps you identify and fix issues before commissioning. That brings us to the end of today's webinar. I hope you found it insightful and that it gave you a clear picture of how Flownex can add value to your cooling system design. We'd love to continue the conversation, so please type any questions into the panel on the right. And if you'd like to explore Flownex further, you can reach us anytime via our website or directly at sales@flownex.com. Also, if you'd like to keep up with the latest Flownex news and features, please follow us on LinkedIn and YouTube.